Okay, so I had a quick question. I had a question regarding Canvas. So when you log into your student portal, there's Canvas here. Yeah, now yours may look a little bit different. So when you click on it, then you will have access to the sites that you are enrolled in. So in this case, this is this unit, structural analysis, and you can see it's a double batch unit because it's got undergrads and postgrads. By the way, undergrads and postgrads are more than welcome to make groups if they want. There is no limitation on that. You can make groups with whoever that you want. So if I click on this, then on the left-hand side, there's a bunch of tabs that you see. So the first one is Home. It gives you an introduction about the unit. This is where you access the announcements. So this is the announcement that I sent, I think, a few days ago. And by the way, there is important information in that. Have a read. This is where you can access some general information about the unit, including EA competencies that we address in this particular unit. So these are the competencies that you will hopefully acquire by the end of this semester. The two documents that I was just talking about are here: study schedule. This is for the whole semester, and this is the document that tells you when exactly you need to attend the lab. And this is a list of your assessments and also what unit learning outcomes they address. So this is a unit outline. You can access this through ECU handbook as well. It talks about the learning outcomes of the unit and the content and, again, the assessments and things like that. Modules is where you have access to now, before I continue, I'm focused, so if you talk, it doesn't distract me. You can all talk the way you were talking just a few minutes ago, everybody talking. I can still teach and continue and do whatever I want to do. It doesn't distract me. However, it does distract the person who's sitting next to you. Or sometimes you tend to speak a little bit even loud. I can hear you. I could hear people talking right on top there. As I said, it doesn't distract me. It doesn't bother me. However, because it does distract other students, and they're here to learn, most of what we are covering is the first time that you see this. So somebody is straining their ears, they're trying to be focused, and all of a sudden, the person next to them decides to watch YouTube or have a chat with the other person sitting next to them or whatever that they are doing. And that's where I have a responsibility to make sure that everybody can listen to the lecture. And I try to do this as soon as I hear somebody talking. Sometimes when somebody falls asleep, I do this again. So that's my way of telling you that you need to stop talking. You're talking too loud for this class. And I'm going to do it once or twice. If you keep doing this, I will then have to call the security to escort you out of the class. Over the past decade or so, I've done it only once. I'm not going to negotiate with you. So this is basically final notice if we're talking. And the next level after that is security. And as I said, it doesn't bother me personally. It's just a responsibility that I carry, that I need to keep this lecture theatre quiet for the majority who are trying to listen. So please do not talk. And sometimes I do encourage you to talk. I give you an example and say, now just try to solve it together. But sometimes you need to be quiet, please. If you have something urgent that you need to attend, you can walk out of the class and come back, please. So modules is where you have all the recordings, all the lecture notes, all the tutorial questions and solutions and all of that. So as you can see, they are week by week. There are some general notes and documents there here that you can read. The next bar that you see there is tutorials. And these are past recordings. One of my past PhD students has recorded most of the tutorial questions that you have. So if you want something very specific about one particular tutorial question, you can refer to these. You have also access to all the questions, all the solutions. Now, the best way to use these questions and solutions is to just use the questions first. It's very tempting to jump to the solutions and see what's going on. And I promise, by the end of the semester, 90% of you, if I give you the solutions, you can walk me through. You can explain. This is what's happening in this line, this is what they are doing here, this is the next step, and this is the answer. You will have naturally that knowledge that you can explain it to somebody else just before the exam. And that's the tricky part. You can still very well explain a solution, and you may at the same time very well fail the unit. Because explaining is one level. Being able to create the solution from scratch with nothing in front of you is it's a completely different level. And they are not close. So you will get to that point to be able to explain and interpret and understand the solutions pretty quickly. Don't be tricked by that. And your phones need to be on silent, please. So you need to practice. Anyway, so these are the tutorials. And then you've got weekly folders as well. As you can see, this is a PDF. I've also actually given you recordings from a couple of past years. We can see 2025 recording is there, 2024. I've got chunk recordings from COVID where I've sat in my office and I've gone through the lectures. They are not activated here because I encourage you to attend. But you still have some access to some of the past recordings. I may disable them on a weekly basis. I normally keep them there in case there is something wrong with the recording. There is at least one backup that you can use if you need to. But that's where you have access to lecture notes and recordings, and they're on a weekly basis. So you've got access to everything. Okay. Then you've got assignments. I've got a self-assessed assignment. I've got, again, you've got access to solutions. I'm always in two minds whether or not to give you solutions, because I don't want you to look at solutions unless you've really, really tried hard to generate the solution yourself before you look at the given solution. I encourage you to go through these at least. I think you've got 9. No, okay, so you've got 12. I encourage you to go through at least 4 of them each week, in addition to tutorial questions that you have. Again, I can't really emphasize enough how important it is to learn about equilibrium, shear force, bending moment diagrams. So you've got access to this tab as well. It gives you some snapshot of different assessments that we have. Okay. And each and every Canvas website that you have is sort of similar to this. Okay, so equations of equilibrium, you're all familiar with these. We've got 3, actually 2 main equations. Summation of forces is 0, summation of moments is 0. Any object in equilibrium in space, you can write 2 main equations for it when it's in equilibrium. And that comes from Newton's first, second, third law. Summation of forces is 0, summation of moments is 0. It's common practice, and we do that in the structural engineering, that we resolve forces and moments into components. So what you see on the screen is a sort of a brief version, if you like, of the global 2 equations that we have. Summation of forces is 0, summation of moments is 0. And there's also another assumption behind what you see on the screen, and that is we're focusing on 2-dimensional structures. So everything that we do in this class is 2-dimensional. Hopefully next week or the week after, when I talk about the structural forms, I can probably explain a little bit more why this is valid assumption. So what you see there is summation of forces. Now we've become a little bit more specific. Summation of forces in x direction is 0. Summation of forces in y direction. Because you can imagine, if it's a 2-dimensional structure, everything is happening in that plane where the screen is. There's nothing out of that plane. Everything, the structure is in that plane, forces are in that plane, stresses that are created, everything is happening in that 2-dimensional plane. And in that plane, we're assuming there is an x-axis, there is a y-axis. So we have a system of coordinates, and we come up with those x and y directions. They are not universal. Sometimes you may see some examples where x-axis is actually in the vertical direction and y-axis happens to be horizontal. There is no rule for it. But in majority of cases, x is horizontal, y is vertical. Yes? Okay, so by doing that, what we are implying is whatever force that we have on that 2-dimensional structure, we are going to resolve it into 2 components, x and y, and we deal with them separately, which is okay. So therefore, summation of forces is 0 has become 2 equations, summation of forces in x direction, summation of forces. There's a particular way that we write this, that is, this is not showing on that. So the one on top, because forces are vectors, yes? So we need to indicate which direction is positive and which direction is negative, because we need to differentiate between a force that is pushing the structure from left to right, from a force that is pushing the structure right to left. So directions are important. And this is the way we communicate with other engineers. We are assuming in this case that forces going left to right are positive. And it does matter because then, if I see a force in this direction, it's plus 10 kilonewton, for example. If I have the same force but in the opposite direction, in my equations, it becomes negative 10 kilonewton. And the same goes with y direction. The third equation that you see on the screen is a little bit more detailed. And that's the equation that we have for moments. Moments, as you know, is a product of force and distance. Yes? So if I have a force of 10 kilonewton and its distance from a point is 10 meters, it's producing a moment of? A moment of? A moment of? That's a very good start. A force of 10 kilonewton at a distance of 10 meters, it's producing a moment of 100 kilonewton meter. But remember, I'm happy and unhappy at the same time with the answer that I received. And the reason is, you always open doors, yes? So, there is a very good scientific engineering reason why this handle is here and is not here. We all know intuitively a handle here would be useless. It doesn't matter how much I push, I cannot open it. Yes? That's the concept of distance. I'm not opening this door by applying a force. Force is just one part of it. I'm opening this door by applying a moment. And you never ever approach a door from here to open it. Because intuitively I know the hinge is here. This is giving me no distance. It doesn't matter how much I push. I need to change direction. And only then I easily open the door. So it's a perpendicular distance that matters. So when I do this, this is the direction of the force, the vector, and this is the distance. When I change direction, I'm actually reducing the distance. I'm not changing where I'm touching the door, but physically, I'm reducing the distance to 0. So it's the perpendicular component of this force that matters. In other words, it's the perpendicular distance. The other thing that matters is where we're taking that moment. And at in this example, we're taking moments about the hinge, where the hinges are. Yes? So in our equilibrium, now you see, it's important to identify where we're taking moments about. So in this particular case, the moment that I'm applying about this point is this force with full capacity because it's perpendicular times that distance. If I ask you what is the moment of this force about the handle, it is 0. So when you look at that equation, we need to indicate in the equation, it's not just the direction, which direction I'm applying the force. Because if I change the direction of the force in this example, and I start pulling, the direction of the moment changes. It will be a moment in the opposite direction. And the moments, the directions are clockwise or counter or anti-clockwise, counterclockwise. So that's why we've got a direction there. And in that particular case, what I'm communicating to you as the next engineer who's reading my solution is that anything anti-clockwise is positive. Anything clockwise is therefore negative. And these are pretty standard directions that we use. But we must indicate A, and A represents whatever point that you decide to take moments about. Because as soon as you change the moment at the point, the magnitude of those moments will change accordingly. And the only way that I can mark your solution is to know which point you have used, because only then I can also calculate the moments and check your solution. Any questions? So this is about positive direction or sign convention for equilibrium. Back to that. I may confuse you now, but we'll spend some time on it. There's another sign convention that we use, not for equations of equilibrium, for shear force and bending moments. That's purely for the purpose of drawing shear force bending moment diagrams. So what you see there is a beam that's been cut. A beam is a continuous structure, yes? We use the method of sections to be able to draw shear force bending moment diagrams. Do you remember this from engineering mechanics? Who has not done engineering mechanics or statics? So everybody's done engineering mechanics, yes? Okay. So you need to look at your lecture notes from engineering mechanics from last semester or last year or whenever that you've done it, and refresh that concept. But I've embedded into these lectures, so you can also look at these. But this is prerequisite. I'm just repeating. So when we cut a beam, method of sections, to be able to draw the shear force bending moment diagrams, then we need a sign convention to decide whether the shear force is positive or negative. To do that, we use this sign convention. Now, some of the books may use another sign convention. In structural analysis, we stick to this sign convention so we can all communicate our solutions. Another advanced unit that I teach, in some of the examples, I've used another sign convention, which is actually opposite this. But hopefully by then, you're an expert and you can quickly translate those sign conventions in your head. So when you cut a beam member to draw the shear force bending moment diagrams, you have two options. You either look at the left-hand side or you look at the right-hand side. You never look at them both at the same time because that's counter-effective. Remember, shear force bending moment diagrams or axial forces are internal actions. You don't see them. It's the way the structure is responding to the external load. External load, you can see them. For example, there's dead load at the top of load that we refer to it as dead load. And in this building, at this moment, these chairs are considered as dead load. We call them dead load because they cannot move. So dead comes from there. There's another one which is called live load. We're all part of the live load here and now at this point in time in this class, because we can all run, walk, we can displace. So live load can be here, can be there, can be there, can be anywhere. That's why we call it live load. This is all external load. But the slab under me that I'm standing on is resisting my weight. How does it do that? By deflection. So the beam or the floor under me, even though I may not feel it, there is always a level of displacement. So it bends a little bit, then it's engaged. So inside that beam, you've seen it in mechanics of solids, there are bending stresses that develop inside the material, shear stresses. And that's how it responds to my weight, and I can stand on it. If the material is really weak for my weight, it will break. Yes? So stresses will go beyond its strength and it will break. What we're interested in structural analysis, that's the main thing that we're interested in calculating the internal actions, namely shear force, bending moment, axial force, or internal torques in some cases, torsion. So we're interested in those internal actions that we do not see. Because we do not see them, this is how we visualize them. We imagine that if we cut a beam, what do we need inside that material so that the beam still is in equilibrium? So once we do some examples, you will remember what I'm talking about. But this is a sign convention. If you cut a beam and you look at the left-hand side, forces that are tensile, going left to right, are positive. Shear forces going downward are positive. Moments that are anti-clockwise are positive. At the same time, on the other side, this is how the two sides of the beam are talking. So if there is a force going in this direction on this side, you definitely, second law I think it is, action and reaction, or the third, you need a force in the opposite direction so that it is in equilibrium. So everything opposite what you see on the left-hand side, on the right-hand side is positive again. So this is a sign convention that we use for shear force bending moment diagrams and also axial forces. Okay. One thing that I'll forget to mention is that every time that you come to class, have a piece of paper, a pen, fantastic, and probably a calculator. I know that you can use your mobile as a calculator. As soon as you look at your mobile, you've got love messages and then you get distracted. So it's good to have a calculator on you as well. Okay, so everyone, grab a pen, a piece of paper, and you need to have access to Canvas, by the way, as well. So have your laptop or whatever other fancy device, anything but your mobile on you as well. Okay, so let's do this. The first part of the question, we cannot do it today, unfortunately. We'll talk about it next week, and then only then you can do it. But it's okay, you remind me next week. Now, can you calculate the reactions? Who can do the reactions? Now, this is part of the class that you can talk to the person next to you only about the question, not about Facebook, okay? If you want to talk and do it together, that's okay. Yes, you can do that. But you know the other method as well, yes? The easiest one, the easier one. Yeah. So you have that freedom, that's okay. How are you going to, now, the last thing that I need is a student sitting idle, just staring at the screen as if something magical is going to happen. If you do not know how to start, talk to the person next to you. And if needed, you can change your seat. Okay, I don't want any one student to be just sitting doing nothing. You either talk to the person next to you, trying to solve it, or you're already busy doing it. Okay, I think I need to give more practical instructions. Are you doing it, sir? You've already done it? Ah, that's good. Sorry, I thought you haven't even started. Fantastic. That's really good. Who needs help? You need help? Ask her. She also needs help? Do you know how to do it? Yes? Do you know how to do it?
No, sure, but I just...
Okay, how can I help?
I'm totally out of control.
What do you mean out of control? Are you dangerous now?
No.
Okay.
About doing.
Okay. Why don't you take moments about this point and see what you get there? Okay. Let me probably just make a start on the board for those who are really still not in the mood. So remember, we've got 3 questions, equations. So why not starting from the last one? But just before that, we need something else, actually. What is the very first step? Before even we can use the equations of equilibrium. Fantastic. Free body diagram. Okay. What does it mean? So a roller we've got at point A. Do you know what a roller is? What is a roller? What type of reactions can it produce? Hey? Vertical or horizontal? That's good. Okay. You know what? I don't know how much force we have there, but I know that this guy can give me RA. You agree? Now, can a roller there produce this? Can it produce RXA? Can it produce resistance in X direction? Oh, before that even. This is X, this is Y. You need to indicate everything. Now, in X direction, a roller, can it produce resistance against movement in the horizontal direction? I need at least one student to answer that question. Fantastic. So therefore, this is 0. That's the nature of a roller, that it can move horizontally. In this case, we can have a roller in the vertical direction. But in this case, it cannot. It can move actually in horizontal. So therefore, there is no resistance. What about point B? Can it produce a vertical reaction? Yes? Okay. Will that go upward or downward? We don't know really, do we? You know what? I know that it can produce a vertical reaction. I'm not 100% sure. I assume this is RBY. Now, at point B, can we have a horizontal resistance? Yes, because it's a pin. Fantastic. Okay. I just assume there is a force going in that direction. Potentially. RBX. Now, any of the two supports that we have, can they produce a resisting moment? They cannot. The only type of support that can produce a resisting moment is a rigid connection, and it's none of the two. Okay, so that's my starting point. So I look at AB. I know that potentially I can have a vertical force at point A, but no horizontal force. I can potentially have a vertical force at point A. I'm not 100% sure in which direction, which is okay. And I can potentially have a horizontal force at point B because it's a pin. What direction? I don't even know, and it doesn't matter. So what I want you to learn from this is that you need to be really brave when you draw the free body diagram. You need to be able to only identify the type of support that you have. If it's a roller, what type of reaction? If it's a pin, what type of reaction? How many of them? And that's all we need. We don't worry about whether they are zero, they are not zero, do they go left to right to left, upward, downward. We don't worry about any of that. We use the equations of equilibrium, which is the next step. Okay? Now, can you help me with the horizontal one? Summation of forces in x direction is 0. This is my positive direction. What forces do we have? Hey? Look at the free body diagram and tell me what horizontal forces you have. RBX. Anything else? Plus nothing equals? Okay, so that already tells me that there is no horizontal force happening at point B. Potentially it can produce it, but at the moment there is no external horizontal force. If it was, then we would have a horizontal reaction at point B. Okay, let's do the next one. Summation of forces in y direction is 0. I'm assuming upward is positive. Can you help me? Left to right. Tell me what you see. RAY, is it positive or negative? Very good, because it's in the same direction of positive. Next. Very good, minus 100, because 100 is going downward. I just assumed that this is positive. So minus 100. What else? Minus RBY. Anything else? Anything else? Equals 0. So from here, RAY minus RBY equals 100. That's all we know. Let's take moments. The third equation. Which point are we taking moments about? A? Huh? A? What if I take moments about point B? Would that be detrimental? No. If I take moment about this point, can I do that? Yes. The problem is, I then need all the distances from this point. So, theoretically, yes, I can, but it's a stupid choice, yes? Okay. So we go back to the screen. We just need to pick a point. But we can pick point A, B, C, or any other point. We normally pick a point so we can get rid of one of the unknowns. And in this particular case, we have two options, A or B, because we have an unknown at any of the two. So let's pick point B, okay? Summation of moments about point B equals 0. This is positive direction. Now help me identify and calculate moments, and let's start from left to right. RAY, does it produce a moment about point B? I think some of you have become conditional. You do not answer my question unless I do this. Okay, RAY, does it produce a moment about point B? Yes. Can you help me with the moment? Times? Positive or negative? Why is it negative? Why is it negative? Very good. So what you need to do is to imagine there's a pin at point B and picture with the direction that we have for the force is if it's pushing the beam clockwise or anti-clockwise about that point. So in this case, we assume RAY is going up, which may be wrong, it doesn't matter. But it's pushing the beam clockwise. Fantastic. So is it positive or negative eventually? Negative. Fantastic. What about the force 100? Positive or negative? Because again, it's pushing the beam now anti-clockwise. So it's positive. What's the magnitude? Times? What about, well, RBX, we know that doesn't exist. That was the first equation. What about RBY? What's the moment because of RBY? Fantastic. RBY is this. You remember? No moment at all because the distance is 0. Fantastic. Okay, times 0, so it doesn't produce any moment. So from that equals 0. RAY is how much? Positive or negative? So when we say it's plus 50, is it, so what is the force again? That's the right answer. In the exam, if you just give me 50 and it has 10 marks, at best I'll give you 5 marks. Because you must say what units you are using. Because it can be 5,000 newtons. Yes? Sorry, 50,000. Because it's 50, yeah. So it must fall, it must have a, followed by that number, there must be a unit. But don't be too smart. If you cannot solve it and just say RAY is kilonewton, I'm not going to give you 5 marks, okay? Okay, 50 kilonewton. Now, we can use 50 kilonewton in that equation and find RBY. So from that equation, what is RBY? Negative 50, very good. So what does it mean when you say negative 50? Hey? It means, very good, that the direction that I assumed, you remember, I just assumed, the direction is wrong. So every time that you use equilibrium and you end up with a negative number, that means the direction that it corrects your direction, in other words. If it's positive, you assume the right direction. If it's negative, it's the wrong direction. Therefore, when you start and you draw the free body diagram, don't worry about the directions. Don't try to guess. But identify the correct reactions. In this case, we know that at A, there is no horizontal reaction. That's important. But the directions are not, because equilibrium will give you the right direction. Okay, fantastic. That's great. Any questions? Anything that you need more explanation there? Okay, let's have a quiz. 2% of your total assessment. Is it good? On a similar beam? Yeah? Shall we have a quiz? On equilibrium. Everybody seems confident, yes? It will be 2 free marks. Any questions?
You do one with a rigid.
Of course we can. Just before that, can we do the shear force bending moment? Okay, so write down the reactions. I'm going to get rid of everything on the screen because I now need space for the rest of the... I'll review different types of supports, and I think it's the next lecture that I'll quickly go through them. So, or you can have a browse yourself if you do not remember the symbols that we use for different supports. So, what I'm going to do now is to attempt to draw the shear force bending moment diagrams. Okay, so far we know that we've got a 50 kilonewton there and another one here. So what I'm going to do now, I'm using the method of sections, but maybe today or in the next lecture, I'll talk about another way of drawing shear force bending moment diagrams. But maybe as a warm-up exercise, let's do it using method of sections. So what I'm going to do, I'm going to cut the beam at one point and look at the equilibrium again and see what I get. So I'm going to cut the beam somewhere between A and C. So I'm going to cut the beam. This is point A. I measure X from point A. Once you do a few examples, you will see that you can measure X from other points as well. But for now, let's keep it from point A. And all I know is, again, potentially, when we cut a beam, we can have a shear force, an axial force, and a moment. So I'm going to call them Fx, Fy, or actually V. Let me call it V. Normally we refer to it as V. And I'll Vx, and then Mx. Every time that you cut a beam, you potentially have an axial force, a shear force, and a bending moment. Some of them may turn out to be zero, but potentially we have them. It's similar to the reactions that we just assumed. The horizontal reaction at point B turned out to be zero. And I know that the force here is 50 kilonewton. Only because I don't have enough space, I just get rid of the units. But you always jot down the units as well. Now, what I'm going to do now, I'm probably going to take moments about point X. That would be my first equation. Because if I take moments about point X, there's no moment from Fx, so Fx is not going to come into my equilibrium. I don't see it as an unknown. Vx is not going to appear in my equation because, again, the distance is zero. It's not going to produce anything. So I'll have only one unknown in my equation, which is a good thing. So I don't need to do the simultaneous equations right at the beginning. But I write the equation properly, and I say summation of moments about point X equals 0, and this is positive. So let's start again from point A. 50 kilonewton, is it producing a moment about point X? Come on. What is a moment? 50 times X. Fantastic. Positive or negative? Because I'm taking moments about point X, it's pushing the beam clockwise, and therefore it is negative. The next term that we need is mx. Mx is a moment, so we need to include it in the equation. Is it positive or negative? Shall I multiply it by a distance? No, because it's already a moment. Yes? Anything else? Equals 0. So mx equals 50 times x. Now I have a question for you. I've come up with that equation. Bending moment at any point, any given point x is 50 times x. So if x is 0, bending moment is 0. If x is 1 meter, mx 50 times 1, which is 50 kilonewton meter. Can I use that equation along the beam to calculate the bending moment? In other words, does this free body diagram that I have here represent the whole beam? No. So for that equation, what I need to write is this is valid for x, anything between 0 and 5. Very good. Because if I cut the beam at any point after point C, what happens? The free body diagram changes. If I cut the beam for any point after point A, there's another force that comes into play. You see? Remember, in both free body diagrams, x is a variable. X can change in both of them. In both of them, you see a 50 kilonewton force going up right at the left-hand side. What you see in one and not the other is a 100 kilonewton force going downward. So if I cut the beam anywhere after point C, another force is part of the equilibrium. When I cut it before point C, I don't see that force. So this is now going to change my bending moment equation. So if I write the same equation, again I have negative 50x plus 100 times x minus 5 plus mx equals 0. This is a completely different equation. I'm now taking into consideration the moment coming from the 100 kilonewton force, which I wouldn't see in the first one. I don't see it in the first one. And for the same reason, I need to cut this beam twice to be able to draw the shear force and bending moment diagrams. And one thing that you need to know is that we never ever cut a beam right where a force is. Out of infinite number of points that we have, there are specific points that we do not use to write the equilibrium because they are not helpful. First of all, any force has got a bearing area. So they are not applied on one force. When I stand on this floor, you may represent me by a vector as a point load, but I'm actually distributed on a very small area. For simplification, we can represent my weight with a vector as a point load, but in reality, it's infinite number of points again. If you cut the beam there, then the philosophical question is whether or not to consider that force. So you can basically cut the beam just after point C or just before point C, and they will both give you exactly the same result. And the reason is the distance is going to be almost zero. So it's not going to change your bending equilibrium. It will, however, change your shear force value, and you will see that mathematically at that very point, it's a point of singularity. So you can't really determine the shear force, which doesn't matter. Physically, it doesn't matter. We don't really care about that one point. So we need to cut the beam twice to be able to complete that bending moment diagram. But if I now just quickly draw what we have, and I urge you to do it after this class, but I'll quickly do it. This is how we draw a bending moment diagram. Again, this is all review of what you've done in the past. So this is bending moment. We indicate the units, kilonewton meter. This is the X. We indicate the units. We carry forward the important points. The first equation is valid only for that first half of the beam, and it's 50x. So for x0, it's 0. For x equals 5, it's 50 times 5. So it goes up linearly because this is a linear equation. It's a straight line increasing from 0 to 250. And I don't write the units there again because on my coordinate I've already mentioned it's kilonewton meter. If you use the second equation, you will see that it starts from 250 and it goes back to 0. And as I said, I urge you to do it after the class. So this becomes the bending moment diagram. And a bending moment diagram is essential for a structural design, whether it's a steel structure, concrete structure, timber structure. It doesn't matter what material we use. We haven't even discussed what material we are using because it's all about equilibrium. So the beauty of this diagram is that with a glance, it tells you a lot about this beam. For each and every point in the beam, now you can look at this diagram and tell me how much bending moment you have and in what direction. It gives you the direction because we picked a sign convention, we are following that sign convention, and it gives us all the magnitudes that we need. What we didn't do was to write summation of forces in vertical direction is 0, and that would give us the shear force diagram. So I'm going to just draw it here for you. In fact, no, I don't have it. So the shear force diagram for this beam will look like this. V, that's the letter that we use, kilonewton, because that's the unit that we are using. It will start from, so again, these are the important points. It's constant and it's 50 kilonewton for the first half. Then it drops to negative 50 for the second half. And I'll leave it to you to write the equations and come up with that diagram. For any beam element, whether it's a standalone beam or it's part of a frame structure, we need shear force bending moment diagrams before we can design it. As you could see, I didn't discuss what material we are using here. It doesn't matter whether it's timber or concrete or precast concrete or steel. Equilibrium is equilibrium. But then we design, and by design I mean we come up with the dimensions and the details of the beam using these diagrams, which is what we do in concrete design, in steel design, in timber design, and the units that come after this one. Now this is a very, very simple question. The next question that I have is basically exactly the same beam with a different loading, with a distributed load on it. So I give you some hints. I won't be able to do it on the board today. For this beam, we only need to cut it once. So in some ways, this is easier than the previous one to draw the shear force bending moment diagrams for. And I'll give you the final answer, but I'll leave it to you to come up with the answer. So we normally have the shear force diagram right below the beam. We use letter V. We have the units. And then right below that, we draw the bending moment diagram. Kilonewton meter. So by having the units right on the axis, for any other number that we put on the diagram, we don't need to repeat the units again and again and again. But if you solve this, you will see that, again, you will have 50 kilonewton reactions, very similar to the previous one. But in this case, the shear force diagram will look like this, starting from 50, linearly decreasing to negative 50, and your bending moment diagram will be a parabolic shape, starting from 0, ending at 0, and the bending moment will be 50 times 5 divided by 2. So that would be 125. But please use the equilibrium, write the equations, cut the beam, and construct the two diagrams yourself. You've got the final answer. Calculate the reactions and then cut the beam once and come up with the equations for V and M. Any questions? I just remembered that I didn't even give you a break. It's coming up to about 3 hours. We normally have 1 or 2 breaks during the lecture. So I just quickly draw the free body diagram here for you. But I'll leave it to you to calculate V and M, X. Now, what I want you to do now is to sit back and look at the diagrams that we have. If you look at the beam in this example, don't do any calculations. Just sit back, relax, and just pay attention to what I'm saying. Look at the beam. Is there any distributed load on the beam? Okay. We normally use the letter small w, small q for distributed load. So let's say W. W is 0. There is no distributed load, yes? W is 0. Look at the bottom diagram, which is the shear force. How does it look like? Constant, yes, for the first half, and then again constant for the second half. You see that? So V is constant. Constant. Okay. Do you see the numbers? It starts at 50, yes? The first half is plus 50, and the second half is negative 50. How much has it dropped in the middle? So what is this drop? 100 what? Okay. Do you see the force that we have on the beam? How much is it? 100. Okay. Now let's look at the bending moment diagram. What do you see? What type? Because it's all mathematics. We wrote an equation. It's a function. It's a function of x. Vx, mx. They vary with x. Yes? We're talking about mathematics here. So this line here, what type of curve is it? Linear, yes? So I just write it here. M is linear. So when we say linear, what does it mean? What is the power of x in that equation? What is the power of x? 1. If I have an equation, a function of x, and the power is 1, if I differentiate, what do I get? Constant. Very good. What do you see above m? Constant. If I differentiate a constant, what do I get? 0. See what the W is? What is the drop in the shear force? The external point load that I have. Okay? Or rather integral of V. Of V. Let's do that. If I integrate V between 0 and 5, mathematically, what is it? This area, you agree? If I integrate a function, it gives me the area underneath the function. From maths, you know that. Can someone calculate that area for me? 50 times, which is 250. How much the bending moment has changed from A to the midpoint? How much? Calculate the next area, this one. What is this area? Negative 50 times 5, which is negative 250. How much the bending moment has changed from midpoint to point B? It has dropped by 250. What is the slope of the bending moment diagram? What is the slope of that line? 250 divided by 5, which is? What is the slope of that line? Tangent of that line, yes? Tangent of that line gives us approximately the slope, yes? So tangent is 250, which is here, divided by that length, which is 5, which is 50. What is the shear force between these 2 points? 50. What is the slope of the other side? Again, 250 divided by 5, but it's negative. What is the shear force there? Negative 50. And you will see exactly the same relationships here. What is W? What is W? 10, yes? Just accept it now. If W is gravity, we call it positive, even though it's going downward. What is the slope of this line? $50 divided by 5 again, yes? And it's negative, yes? So basically, dV over dx is negative W. What is the area underneath the shear force between these 2 points? How much area do we get here? If I integrate shear force, which is basically calculating that area, how much is that area? 50 times 5 divided by what? How much the bending moment has changed between A and the midpoint? 125, which is this area. What is the slope of bending moment right in the middle? 0. What is shear force at that point? 0. So in other words, dm over dx, which is the first, if I differentiate, is V. How much area you've got there? Again, negative 50 times 5 divided by 2. But this time negative, 125 negative. How much bending moment has changed from this point moving to this point? Negative 125. So, just before I wrap up, method of section, which is a very solid way of calculating reactions, shear forces, bending moments, is still applicable. We want to be a master of method of sections, calculating shear force, bending moment diagrams, using equilibrium, yes? But over a very short period of time, we want to take off from that foundation and use this method. Because instead of spending, let's say, 25 minutes to 35 minutes in your mid-semester test on one of the questions to draw the shear force bending moment diagrams using the basic method that you learned in engineering, what's that unit? Static, engineering mechanics. Instead of spending 25 to 35 minutes in the mid-semester test, within a couple of minutes, with minimal calculations, you can draw shear force bending moment diagrams. And then you can proceed to the next question. And in fact, the way I time your mid-semester test is not going to be based on method of sections. It's going to be based on this. We will talk about this again. But I do want you to look at the remaining of the lecture notes that you have here, because it's mainly engineering mechanics, but I want you to also look at all these examples, and then obviously you come back with your questions, and then you get to these slides, 41, 42, 43. These three slides are basically these relationships that I just pointed out to you. So within a few weeks, within the first 3 weeks, we want to remember everything that we learned in engineering mechanics about equilibrium, shear force, bending moment. But very, very quickly, we want to move towards this quick way of drawing shear force bending moment diagrams, which are based, it's very solid. It's based on the mathematical relationship between external loads and what happens inside the structure. Mathematical relationships. If you integrate one, gives you the other. If you differentiate one, it gives you the other. Very solid relationships. But it's going to save you at least half an hour per question. And guess what? You go for an interview for a structural engineering position. HR always sits there. But the leader of the team will also come and attend. And they will ask you questions. They are not going to ask you sophisticated design questions. They talk to me. I know what they are going to ask you. They ask you about this. They give you a simple beam, maybe a continuous beam, because we learn about indeterminate structures in this unit as well. And they quickly want a reaction, a shear force, a bending moment. And look at how you approach it, how deeply you're familiar with the concepts. Remember, the fancy topics, design questions, you can always learn them. You use a lot of pieces of software, there is a lot of aid that you can use. Concept, that's what stays with you. And that's what you need. You need the basics, but very, very solid foundation. If they see that you've learned the basics and you can maneuver with these equations, you can skillfully use them, that's what they need. Because they can train you. There's always, these are graduate positions. They will train you. They want to see two things: your character. Are you an arrogant, self-centered, whatever character? Can you work with others? When they call your referees, the first question that they ask is, about your character. They don't worry about your fancy transcripts. That comes second. The first question that they ask, how did they manage the teamwork? Because now you have to work with another 50 engineers, different backgrounds. How do you handle the dynamic of the team? That's the first thing that they're interested in. So if you attend, if I've seen you how you conduct yourself, not me as an example, we can give feedback to them. Then they will have confidence and they will pick you. Or I say, I've never seen them in the class. I don't even recognize the face. That's not good. And the next is the basic stuff. Structural engineering, this is basic stuff. What I teach in timber, steel, that sort of thing, they would rarely ask you questions within the 10-minute interview, 15-minute, the technical part I'm talking. There's no time for that type of detail. But they will talk about the structural form. Do you understand the structural forms? We will have one quick lecture on the structural forms, but that one lecture is going to help you in your interviews because that's conceptual. Because the first thing that you do to create a structure is what type of a structure you're going to pick. That takes a hell lot of understanding of concepts. And then this is stuff. So within the first 2-3 weeks, and that's why I've given you a self-assessed exercise. I'm not going to mark you. You are going to mark yourself. You've got the solutions. Do not look at the solutions. Even the microphone is tired now. I'll wrap it up. Do those questions. Mark yourself. Give yourself a week to be able to generate the solution. Don't look at the solutions. Do more examples so that you can do these. Then mark yourself. Write down the solution, then put the solution in front of you, and then mark yourself. And hopefully within the first 3 weeks, you will improve. You're going to mark yourself. You're going to assess yourself. And then tutorials, examples, book, and attendance. Any questions? Thank you very much. You did great. You were really patient with me today. Sorry that we didn't have any breaks. We will have breaks from next week. And I'll hopefully see you all next week, and the week after, and the week after, till we wrap up the semester. Thank you all very much, and all the best.